Okay, how do you guys want to do it in shifts, like yours first and past the center? You want to do yours first? What's that? Let's just have them pass. Don't walk around. It's like too long, right? So, if you're in Morteza, we'll do that first. Morteza. Okay, and then here comes Pollock. Whoa, don't go too fast. Okay, so what we're going to do now is we're going to start a cycle of collecting just one major homework a week on every Wednesday. Okay, so but I'll be putting it up, gradually so you can get started on it. So I'll put some homework up tonight, and then but it won't be all of it will be due next Wednesday. But don't wait till Monday or Tuesday to start. That won't be wise because it'll be a whole week's worth of homework. So you got to work on it gradually, right, over the whole week. If you wait till the last second, then you'll have maybe forgotten a lot of the stuff from 5-6 days ago, and then you'll have too much to do. So you got to be working on it starting at over the weekend at the latest. Okay. Questions about homework? Okay, and remember when you're doing that written homework, you're following those guidelines on the Blackboard announcements. Okay, putting the lines where we ask you, labeling the tops of the pages. Please do all that stuff. It makes it much easier for us, and then it'll be easier for you when you get it back. You'll be much more organized. Okay, so we're talking about, let's review. Well, we're on this. We've kind of completed the journey of, or figuring out, developing. You know how fast something is changing at every moment. You want to know how much you have at every moment. And this was kind of our conclusion to that development of that, right? And so half of all calculus is really about this question. You know how fast the quantity is changing at every moment. You want to know how much you have. Okay? So just real quickly, just take 30 seconds, get a partner. Everyone's talking to somebody. Identify the first function, explain what it does. Then identify the second function, explain what it does. Everyone's got a partner. Everyone's... Okay. First function. What is it? What's the first function? Yes, sir? Is it total or net? Total, right? And exact or approximate?
Exact.
Right, exact. You should have said exact total accumulation. Exact total accumulation. And what does it do? What does that function do? Or what does it give you, right? What does it give? What is exact total accumulation? What does that mean? That's what we're saying by answering that question. Anyone want to give it a shot? Someone in the back? Someone in the front? Yeah.
Showing the accumulation from A to X and then adding it to all the accumulation that happened before A.
Right. So f of A is all the accumulation that happened before x equals A. And then now we're going to start accumulating bit by bit, right? And it's going to give you the total amount of the quantity in question at the current value of x by taking everything up to A as a lump sum and then accumulating bit by bit from A to x. That's what the integral does, right? Okay, what's the other function? How about someone up here? The next function is, which one is it? Exact net accumulation. Okay, what does that do or give? Doesn't give total amount anymore. What does that give? Right, between a and x, right? Or the amount of change since a, right? So it's the amount of change since a, or the accumulation starting from a, going out to x. Okay? Very good. All right. And so if we want to write a total accumulation function or an exact net accumulation function, what do we need to do that? Because this is going to be, we're going to have this over and over and over again throughout the semester. We're going to need to write an exact one of these two functions. So what do we need to write that? What's that? The rate of change function, right? If you have the rate of change function, boom, then you've got these. Now the only other thing you might need is if you're writing exact total accumulation, you need the rate of change. You'd also need your starting amount, right? Or this everything before A, right? Everything you've gotten before A. So we need the rate of change function. That's what we need. Okay, so if we want to write an accumulation of area function or an area accumulation function, what do we need to write that? Rate of change of area, right? Rate of change of area. So whatever quantity you're dealing with, if you want to build a function for a total amount of that quantity or a net accumulation of that quantity, then you're going to need the rate of change of that quantity. The rate of change function, right? The rate of change function. So that's the rate of change of area. Okay, questions on that review? So we started area, so we said we need to determine the rate of change, and then we need to investigate what happens when function values are negative. Okay, we'll talk about that a little bit later. So we were looking at this last time. And so so I'm interested in the area of the blue shaded region. Okay, so I've got here on my x coordinate is in inches, and my y coordinate's also in inches. Okay, and then I'm interested in the area as a function of x. So now this A means area, not approximate accumulation. Before it meant approximate accumulation. In this context, I'm using it for area. So that A is going to be in inches squared. And so what am I looking for? I'm looking for the rate of change of area. And I'm starting out with a real simple example. And we said last time, the rate of change of area was what? Remember what we said? 3. Okay, so let's just check that a little bit. So if that's true, then say for a change in, so we can check that by using dy equals mdx. So if I get a change of, so here I'm going to come here, I'm going to change, okay, I'm going to change the x value by 1. So I'm saying I'm going to go from 2 to 3. That's a change of x of 1. From 2 to 3. How much did the area change? Did it change by 3? Did I add 3 inches squared to the area when I changed x by 1? So does that check out? Does that check out? We said if the back and forth between pen and here, so I gotta make sure I got that. So does that check out? I changed the x by 1, and we said that the area, so this should be dA. The area changed by how much? Which would mean that the rate would be 3. All right, now I'm going to change the where is it? There we go. Okay. Pause. Now I'm going to change the area, say, or the x by, I'll start at 1.5, say, and I'll change it 2.5. So go from 1.5 to 4. So x changed from 1.5 to 4. So I want you to, if x changed from 1.5 to 4, I want you to figure out what is dx and what is dA. All right? So x changed from 1.5, here's starting x, to finish x at 4. What is dx and what is dA? Go. So I'm going to go from 1.5 to 4. Here it is. There's starting x, finishing x. How much does x change? 2.5. And how much does y change, or how much does the area change as you change x from 1.5 to 4? How'd you get 7? So the area increases by 7.5. So this should be like pretty easy and painfully obvious that our rate of change is, therefore, what times dx equals dA? Times 3. So that's just kind of reviewing last time, checking that out. Okay, so the rate of change is 3. What's the units on that? 3 what? If it's a rate of change. Yeah. He wants inches squared per inch. Is that right? How much does the area change? Area is inches squared per inch of x change, right? Per inch of x change. So can we just cancel out we got inch squared and inch. Can we just make it 3 inches? Yes or no? No, why not? Because it's rate of change, right? Rate of change. We want to know how much does the area change per unit of x. If we just change that to 3 inches, well, 3 inches is designating a length. Just a single quantity of a length, not a rate of change of area with respect to a changing length. We want to leave that as inches squared per inch. Okay? So how does that rate of change relate to the function f? So now I've got this function f, and I'm sweeping out area. How does that rate of change relate to f? Tell me your name right here. Yeah, in the red shirt. Catherine. How does rate of change, this rate of change of 3, relate to the function f?
So, if f is the area, really, yeah, the total accumulation area, when the rate of change is 3 inches squared per inch,
Okay.
you know that f relates to every time the area is increasing. Like when you draw like the integral, like that's the function.
Okay. So how does this 3 inches squared, how does that relate to function f? It is the same, right? It's the same number, right? Is it the same units? What are the units of f? Are the units of f inches squared per inch? What are the units of the dependent variable of f? Inches squared per inch? No, just inches, right? Well, now it doesn't work. All right, here we go. Right, so our rate of change of area is 3 inches squared per inch, but f of x would be in inches, right? Because it's your y coordinate. All right, so here's the trick. To get the rate of change of area, we're going to use the value of the function, but we got to remember that it's a different unit, right? It's going to be a different unit. So all we're doing, so to get that rate of change of area, we're going to pick off the value of the function, but units are different. We're only going to take the value and just, use our intelligence and our smarts in the situation to say, okay, but I know what the unit of that rate of change should be. It's not going to be inches. It's going to be inches squared per inch. Now, mathematically, it works out to the same, but we want to communicate that this rate of change of area is in inches squared per inch. Okay, so we're going to use that function value to grab the number and call it our rate of change, but then use the right unit for the rate of change, inches squared per inch. So, but here's the real test. So that was easy because that was constant rate of change, right? Because it was a constant function, we had constant rate of change. So here's the real question, now I've got this function that's sweeping out area, and that function value is changing. So now, what's the rate of change of area going to be? How is that? So this is kind of more realistic situation, okay? And we're going to do the same thing we did last time. So we're going to figure out if the function is changing, what about, and the rate, so therefore the rate of change is changing. What is the rate of change of area now? What is the rate of change of area now? So here's an example. Let's watch this. It's in your textbook. So this is showing we're sweeping out the region, right? Using the function, between the function and the x-axis. So now look at what's really going on here. We're going to zoom in right there. And what do you see? Does this look familiar? What have we done to the function? Yeah, so we've made it a pretend function by making little steps. Okay, we're going to zoom in again. So at a micro level, this is what's happening. Okay? Can we figure out the rate of change of area now? Yeah, because it's just the same thing we just did with the 3 example, right? So for any little delta x or any little change in x, we got a constant function. So we know how to get the rate of change. What will the rate of change be if the function is constant? What will the value of the rate of change be? The value of the function. That's what we figured out, right? That value of the function 3 ended up being the rate of change of area as it was being swept out. So now if we just do another pretend function with the little steps, we can apply that. Okay, so as I take attendance, I got some questions for you. First question is, in this situation, or let me go back here. All right, so the blue region, or the turquoise region, is denoting what we're talking about. So you're looking at everything that's been shaded blue so far. That's where we're pausing, right? We're pausing all the way to what's shaded turquoise. Okay, so you're going to answer. What is the value of delta x fixed or varying, and what is its current value? And then is the value of dx fixed or varying, and what is its current value? And then is the rate of change of area fixed or varying, and what is its current value? All right, so that's your little task here. I'm going to take half of the attendance. Everyone's talking to somebody. The TAs will circle around, make sure you're on task. The more conversation's going. Okay, how about right here with the black water belly? Yeah, what's your name? What is it? Anna. Tell me about delta x. Do you think it's fixed or varying?
Fixed.
Okay, fixed. You agree? Delta x is fixed. By definition, that's what we said. We're going to start by chopping up the x domain into constant delta x values. Right. What's its current value, Anna? Yeah, this is 90, 91, 92, 93, 94. Over 1.5. Agree with that? I think it's a little bit more over 2, right? Because we're here like 91 and a quarter, and here we're like 93 and 0.6 or something. So yeah, so 2.2-ish? 2.1, 2.2, 2.3, something like that. Okay? Cool. Value of dx. Okay, how about up here in the maroon jacket? Yeah, that's you. Dx, what do you think? So in this situation, is it fixed or varying? It varies through the intervals, right? Dx starts at start of a delta x interval, and it varies through the interval, then it starts over. So what about right now, what is its current value? What do you think? He said 1-ish. Dx is 1-ish. Would you agree with that? I would agree with that. It's 1-ish, maybe a little less than 1 or something, right? But about 1. Because why? Because dx would be from here start of this current interval to the current value of x would give me my dx, about 1. Does it make sense? And that varies. As x increases, dx is varying through intervals. So what is dx varies from what to what? What's the lowest possible value of dx? 0 at the start of a delta x interval. It's 0, and then what's the maximum value? So it increases, and then it hits a maximum value of delta x, right? Delta x, or 2.2. And then you start the new interval. Dx is 0 again, and it increases with x, right? So dx is increasing, always from 0 to delta x, then 0 to delta x, then 0 to delta x. Does it make sense? Okay, the rate of change of area. Let's see, how about up here in the bluish purple shirt? Yeah, that's you. Rate of change of area. Do you think that's fixed or varying right now? Varying. Okay, what do we think? Agree? So what about just in the moment, right? So just right here. Is it varying if we just are staying right around here? Fixed or varying? Yeah, so within a delta x interval, it's fixed. But then those change, right? Then those constant, as you go to the next step, you get a new constant rate of change of area. So you really can answer that either way. But at this moment here, say between 94 and 95, is the rate of change of area fixed or varying? Fixed, right? And what is its current value? 1.6-ish, a little bit more. Maybe say 1.61, about 1.61. Does this make sense? Super important questions that you understand what's happening here. Yeah?
What's the difference between delta x and dx? I might have just forgotten that.
Okay, what is delta x?
16.
It's before we start, we chop up the x intervals into a fixed value, right? And then what's dx? Yeah, as x increases, so here comes x. What's dx right now? Here comes x, ready? What's dx right now? 0. And now dx is increasing. dx is increasing from 0 to 2.2-ish, delta x. And now what's dx now? 0. So dx changes with the current value of x through those delta x intervals. Is it better? Okay. So that's this picture I'm showing you, right? So here's a particular delta x interval. And then dx, in the current interval, dx is this right here, up to the current value of x. Okay, so notice that in this delta x interval, the constant rate of change of area is about 1.61. And where are we getting that from? Where does the 1.61 come from? The value of the function. Is it the rate of change of the function? No, it's the value of the function. This is like half of you, like if history repeats itself, half of you will blow this on the test. The area, rate of change of area is not the rate of change of the function. It is the function value. It is the function value. Okay? So in this case, 1.61 is our rate of change of area. Okay, back here, what was the rate of change of area? About 1.58, right? About 1.58 is the rate of change of area. And that comes from the value of the function, right? The value of the function. So as we make the delta x interval small, do you see what will happen? How will we get that rate of change of area? So let's look at it here. So now we're back to a continuously increasing function. Now just think of that function as a zillion little steps. A zillion little steps, each with a little constant rate, which is essentially the same as what we have there, right? So when x equals 0, what is the rate of change of area? At x equals 0, what's the rate of change of area? 1, right? How much does the area increase? It's going to increase by, when x is 0, it's going to increase by that much. You make a little change in x, you're going to get that much more area. back and forth and back and forth. Okay. All right, so now what about at 2? So we get to x equals 2. What's the rate of change of area now? What is it? Okay. I thought you said under 2. So do you see that the rate of change of area at 2 will be? Like 2.4. Imagine right there, that's just a teeny little step, teeny little constant value of the function. And so then as you vary through that interval, your rate of change will be 2.4 of area. Okay, what about at 3? So now over here, x equals 3. It's the rate of change of area at x equals 3. About 3. So it's still, even when the function is changing, your rate of change of area changes right with it. It's the value of the function. Was there a question up here? Yeah.
Yeah. So you said the rate of change of area is not the rate of change of the function.
Right.
So but at 0, like at 0, like the rate of change of area is 1, like you said.
Uh-huh.
What would the rate of change of the function be?
Whatever the change in y over change in x is over that function, right? So we could zoom in right there and look at a little change in x and its corresponding change in y. And here it happens to be close to 1, but just coincidentally. But that's not why the rate of change of area is 1. The reason the rate of change of area is 1 is because the function value is 1. Because we could say the same thing up here. It's still, the rate of change of the function is still about 1 here. It's not much different than it is there. But what's the rate of change of area here? 2.4. 2.4. Is it better?
Yeah.
Other questions? Okay, cool. So here's a function. Capital F of x equals the integral from 1 to x of little f of t dt. And here's my function little f, okay? So what is this integral function doing? What is it calculating? So if you look at, so this little f function right here is this function little f. So what is the function capital F of x? Cat toy. So I want to explain everybody's talking to somebody this time. If you have to move seats, you move seats. And so my TAs are going to make sure. In the yellow shirt in the very back. Tell me your name. Alan? Tell me, what did you guys talk about? So what, if you were to explain that function to somebody, tell me what is that function doing? Right, okay. Of what? So yeah, so this is net accumulation, starting from 1. And what's getting accumulated? What quantity is getting accumulated? Little f? You're saying that's getting accumulated? That's the little f of t would be what in this situation? Rate of change. So that's the rate. So the rate of change of what quantity that's being accumulated by this function? Yeah, so this is exactly what we're talking about. That if it's the function value, then you're accumulating area, right? So this is the net accumulation, exact net accumulation of area starting from x equals 1. And specifically what area? The area squeezed between the function and the x-axis, right? Is that what you talked about? So it's the exact net accumulation of area between the function and the x-axis starting from x equals 1. That was a full explanation. Okay, so now we got to investigate here. Notice that here our function values are positive. And then to see it better here, I got another view here to look at. So notice here, function values are positive, shown by the fact the function's above. But here, function values are negative, where it sweeps out the gray region, right? So what, in terms of this integral then, what's going to be the impact of the fact that here those function values turn negative, what's going to be the impact on the integral? What's going to be the impact on the, yes, sir?
Would you say that the accumulation area would still be positive because area has to be a positive quantity?
Okay, good. So he's talking about area has to be in a positive quantity, and so if we were truly accumulating area, what would that function be? Would it ever be decreasing if we were truly accumulating area? It would always be increasing, right? Because area is a positive thing. There's no really negative area. Now, is that what the integral does? Does it keep increasing? Why not? We get here past 2, and what are the values of the function? Negative. Okay, so what will an integral do if your rate is negative? The accumulation. Yeah, Anna. Okay, let's just focus on, yes, you're correct. Let's just focus on this part. When the rate of change is negative, what will an integral accumulation function do to your amount of accumulation? The accumulation goes down, right? Accumulation will be going down when the rate is negative. So does this integral function, does it give us area? No, it doesn't really give us area because when this rate of change is negative, what's going to happen to the capital F function when the rate is negative? It's going to decrease. But area is positive, it always increases. So we want to, this is not, technically it's not area. We want to call it, what we're going to call it is a new quantity called signed area. Signed area, that can be positive or negative. It can increase or decrease. That's what the integral will do. Whenever the function values are positive, what happens to signed area? Whenever the function values are positive, what's happening to signed area? It's going up. It's a positive contribution to the integral function. Whenever the function values are negative, what's happening to signed area? Going down. It's kind of like we're removing that area now. It's like we're subtracting. She said difference of areas, right? So here in the green, area is going up, and when we hit 2, now this value of signed area is going to start decreasing. So what about the value of the signed area, the value of this integral when x equals, so just predict, what do you think about the integrals, or f of 3? F of 3 would be the integral from 1 to 3, f of t dt. What can you say about that? What would you think? Negative or positive? Negative. What about f of 2.2? What can you say about that? Do you think that's negative or positive? 1 to 2.2? Positive, because we haven't decreased enough to overtake the green, right? So the green gave us a positive amount of area, and when we enter into gray territory, the signed area starts going down from there. So at 2.2, that amount of decrease has not overtaken all the increase we got before in the green. But by 3 it has, right? But by 3, the time we get to 3, so this is going to be less than 0, right? This one would be greater than 0. Does it make sense? Okay, so when we just have a straight up net accumulation function related to area, it's not technically area, it's signed area. Whenever your rate of change or your function value is positive, you're adding to that quantity. Whenever the rate of change or the function value is negative, you're taking away from that quantity. So that signed area can be positive or negative. It can increase or decrease and have a negative or positive value. Okay, so I have a little exercise. Any questions on that? Should make sense. Yes, please. Oh, yeah, so if we want the area function, so say I want the area function. How do you want to do that, Zane? Integral from? I want the function, though. I want the function. 1 to x, okay? Yeah, so if you took that function f, you see if you took that function f and took the absolute value of it, Do you see that that would give you area, or what we'll call unsigned area, which is the same as just straight up area? Yep, good point. So unsigned area is the same as area. Always positive, always increasing if you're adding to it. And that would be if you took your rate of change or your function, and for every value of the function you made it positive, then we would get the green, we would keep adding, and then when we got to the 2, then we keep adding the gray, because now your absolute value of f is positive. Okay, so I want to give you a situation here. So here's 2 functions, p and q. So I'm going to start taking attendance. You're going to watch the numbers, watch their values. Watch the value of p, watch the value of q. And I want you to determine what is function p, what is function q, and then can you write a statement that brings them together, right? Can you write a mathematical statement that brings them together? And I'm going to start roll. Go. So what is p? What is q? And then can you write a mathematical statement that brings p and q together in the same statement? Where's Lauren? Lauren, tell me, did you figure out one of these functions? Capital P or q? Take your pick. She said q is the signed area. Agree? So it's tracking what? It's tracking area, but a positive whenever the function is positive, but then negative, or it'll decrease. That signed area will decrease whenever it's negative, whenever the rate is negative. Agree? All right, what about p? Maya, where's Maya? What about function? What's that? P is unsigned area? So if it were unsigned area, what would its values be over here? So here it is at what? Yeah, so it's negative and going down, so it can't be unsigned area. What is p? Yeah. Little f. She's saying little p is the same as f. Agree? And so what does that mean for the area? What is capital P? Rate of change. Okay, so now we're going to write it. So how can you write these together? Let's see. Somebody tell me your name right here. Nope, behind her. And the glasses. Right here with the glasses on your head. Right here. Maddie. Okay, tell me. We said P was the signed area. Sorry, Q was the signed area, and P was little f, or the rate of change. So how can we write a statement to bring those together? We'll do x, right? So n is just the variable in the GC. Q of x equals? If we want the function, so I want every single unsigned area. 1 to x. We can use x is not okay here, right? So it's anything but x. So n is fine. We'll do p of n. That's fine. dn, right? What? Change in y equals rate times change in x. This is m dx, right? That's what every integral you've ever looked at right there. That's m dx. Rate times little change in the independent variable. Yes, sir?
Oh, could you explain why it wasn't okay to put the x?
Yeah, because x is like the value of x here. And so for any given x, we want to accumulate from the start to there. Right? So for any given x, we need all the function values in between to get that amount of accumulation. So we need a different letter. It's an x value, but it's a different letter that shows it's not x, the right side, but every x starting from a up to x. Is that better? Yeah.
So it's not like what x represents. It's like
it's every x value between there and there.
Right.
And x is specifically the right-hand one. Yep. Okay, are we good on that? Okay, so now I got another one for you. Another quiz, harder. So G and H. So now I'm going to keep going on attendance. I want you to figure out what's the function G and what's the function H. Go. X. G of X. What's G? Is it signed or unsigned? It's signed. What's different about it than Q? How's it different? It's signed area. Say. So what's different about it? It starts at 2 this time. It starts at 2, but same rate of change and still signed area. So that signed area will be negative. It'll accumulate negatively because all those rates are negative through there. See that? So the value is negative the whole way. Okay, what about H? Unsigned area starting from 1. So we could do it this way. And what I wanted to do was write it a different way without absolute value. So maybe in recitation tomorrow you can do that. Write this, no absolute value. How would you do it? No absolute value. Write this, the unsigned area or the true area function. See you Friday. Keep checking for homework and get going on the homework.